Hello, Jeremy here in a video on wave-particle duality in quantum mechanics in only 4 minutes. Oh boy. So what is quantum mechanics? Simply put, it's small-scale physics, specifically at the subatomic level. To discuss wave-particle duality, we must first review what particles and waves actually are, according to classical physics. Particles are localized in space, and two particles may interact by bouncing off each other or sticking to each other, but they cannot occupy the same position in space. Waves, on the other hand, are spread out and they can interfere with each other, as shown in the example at the bottom right. If two crests meet, they reinforce one another to produce a higher crest. Similarly, say a crest and a trough cancel each other out. To explain wave-particle duality, we shall look at the famous double-slit experiment, which consists of a wall with two narrow slits, placed in between a source of either particles or waves, and a wall that detects where the particles or waves arrive. Let us first look at the simpler case of classical particles incident on a single slit. Some particles are reflected by the wall, and the ones that make it through the slit are detected as a narrow distribution by the detector. Now, what do we expect when such particles are incident on two slits? Ignoring the reflected particles, we just get the result we have for a single slit at two locations. In other words, the distribution curves add. Simple enough. Let us now look at waves in classical physics. Let each red line in the diagram represent the crest of a wave, and the space in between the lines represent the troughs. Imagine it like looking down on the ocean, seeing the wavefronts incident on a beach. Without going into too much detail, the waves spread out in a semicircle once they pass through the slit, and the amplitude measured at the detector, that is, the height of the wave, forms a centered but more spread out distribution. Now let's have some waves, say light waves, be incident on two narrow slits. This deserves a little more attention. Note that at each marked point, the crest coming from one slit coincides with the crest coming from the other slit. On these green lines, crests coincide with crests and troughs coincide with troughs to produce waves with larger amplitude. In between the green lines, crests coincide with troughs and vice versa, cancelling each other's amplitude. Note that this pattern also extends to greater angles. This wave distribution is, however, still a well understood phenomenon in classical physics. So what's so different in quantum mechanics? Let us take a step back in time to the early 20th century. Classical physics could not explain blackbody radiation. This problem was named the ultraviolet catastrophe, as classical physics predicted that the energy of thermal radiation tends to infinity at higher frequencies. Planck managed to solve the problem by suggesting that light comes in packets of discrete energy, called quanta. In light of further experiments, Einstein took the idea one step further by claiming the existence of light particles, which he called photons. So, light is a wave, but granular? Indeed, this is what experiments seem to suggest. De Broglie then suggested a grand symmetry in nature. He hypothesized that just as a photon has a light wave that governs its motion, a material particle has an associated matter wave. This is wave-particle duality. In our macroscopic life, these waves are too small to be detected. Things are different, however, at the subatomic scale. Conducting the double-slit experiment with electrons, we indeed get the distribution of classical waves, but the granularity of particles. The distribution is unchanged even if we shoot just one electron at a time. The perhaps most popular interpretation of all this madness is the Copenhagen interpretation. It considers the matter wave as a probability wave in which a particle localizes itself during an interaction. This probability interpretation naturally leads to the issue of indeterminacy, meaning that we cannot state with certainty what a particle will do, but only give probabilities. If all of this seems philosophically troubling to you, you're not alone. Einstein himself was troubled, leading him to exclaim that God does not play dice. Thanks for listening.